Hello, this is my Physics 2211 Lab 2 report on the motion of a falling object. Quick overview, we are tracking the motion of a falling object starting from rest, and the fundamental principle at play is Newton's second law, which is defined as the net force is equivalent to the change in momentum over change in time. An electronic tool is used for a tracker, closed script, and a camera. A few important starting equations are the definition of momentum, which is the product of a system's velocity and mass. Average velocity is defined by the displacement over the change in time, and with some algebra we can get to the position update formula, which we will use in our model. A few implications of Newton's second law is that since it relates the rate of change of a system's velocity over a certain time interval to the ratio of the total net force acting on the system to the system's mass, we can use some algebraic manipulation and get two important implications. We use this velocity update formula in the model, and this is the momentum principle as seen earlier, the fundamental principle. So the magnitude of the force of gravity on an object is defined by its mass times the gravitational constant g when close to Earth's surface, and for the purpose of this lab it is, and the direction of gravity is downward in the y direction using this unit vector. So this is the representation for the force of gravity. And for the purpose of this lab, we define the drag force magnitude to be proportional to some constant b to the square of the system's speed, as shown here, and in the positive y direction, opposite of gravitational force. So this is for this lab. The constant b was chosen to match the final position data of the system through repetitive testing in the model, which I will show. So the goal of this lab is using Newton's second law. The goal is to use a computer model to predict the observed motion of an object using two models, one with only gravity and the other with gravity and drag. So let's look at the video, and here are a few notes for the paper ball, everything else in the room being the surroundings, orientation, calibration, and frame rate. So here is the motion itself. Here's the ball being tracked. As you can see, it spreads out more as the change of position increases more, and we'll look at these graphs momentarily. So here are some initial conditions. The mass of the paper ball, 0.05 kilograms, starts at the origin, initial velocity of 0, starts at time 0, gravitational constant, and everything else. And this is the constant that was calculated through some repetitive testing to match the final position. Here's a code equivalent. And here's an updating loop for predicting motion. It goes up to the time interval that the motion was captured. Here's the forces of drag and gravity, which we discussed earlier in code form, and the velocity and update positions. And a quick note, when b is 0, the net force is only the force of gravity. So let's look at the model. So here's the code I mentioned, and we will first look at when only gravity is the net force on the system. Gravity in this case is shown by this vector in the negative y direction acting on the system, which is the ball. And as you can see, as time progresses, the ball will move faster downward, as we can see from the position model. And now looking at just the gravity and the drag force acting on the system, you can see gravity still pointing down in the negative y direction and still represented by this constant vector, but opposing it in the opposite direction is the force of drag. And eventually, as we will see, the force of drag approximately is about the same as the force of gravity. So that means it will be moving at a certain velocity, which we will examine momentarily. So here's the experimental versus predicted position. The blue line is the experimental data, and the red dotted one is only the model with gravity. As you can see, it overpredicts the position because it does not have drag opposing it. But when you add in drag, which is the black dotted line, you can see that it very nearly approximates, especially near the end because we chose it, very nearly approximates the experimental data. So we can say it's a pretty good fit, even with the speed squared being proportional to the magnitude of the drag force. So here is the predicted experimental versus predicted velocity comparison only with gravity. As you can see, as time progresses, it does not approach a constant velocity, but when you compare the velocity versus time graph for gravity and drag, it does appear to approach a constant or terminal velocity. And from the gravity one, it will not approach a terminal velocity because there's no drag force, and the terminal velocity would be when the drag force is about equivalent to the force of gravity. And additionally, if we have different initial velocity scenarios, as you can see with these four graphs, the approach terminal velocity will still be about the same in every case. So any initial starting velocity will not change the terminal velocity reached. Few assumptions for possible sources of error. While modeling the motion, I had to make a few assumptions. The constant gravitational acceleration because we're closer to the surface. No lateral movement. I did have to make sure that it was only going down in the y direction, and the initial speed was actually 0. A few sources of error were the position variance when I was trying to track the data in the tracker, the rotation of the axes from -1 degrees from the horizontal, and an inconsistent surface area of the ball for the drag force. Thank you.